Welcome back to compilersutra. This is the second video in our series of creating libraries in C++. In the first video, we answered a simple but important question. What are libraries and why do we need them? Today we will take it one step further. First, we will break down the different type of library you will encounter in the system programming. Then we will get practical and build first static library together. So let's start. First one is static library. File extension is .a in Linux and .lib in Windows. These are linked at compile time. Once your program is compiled, the library code is copied directly inside your executable. And dynamic library, file extension .so in Linux and .dll in Windows and .dylib in macOS. These are linked at runtime. The code lives outside your executable and many programs can share the same library in memory. And header-only libraries, .a or .so file, they provide only header file such as .s and .hpp, often using templates. The compiler pulls in the actual code during compilation. Fourth is FAT library, mainly used in Mac OS and iOS. The single .a file contains multiple architectures, for example, Intel, ARM, code in one file. Useful when distributing a library that should run across different devices without the developer worrying about which CPU architecture is used. And fifth one is system library. They come built into your OS or compiler, example libc, libstdc++, and libm. Without these, even printf or cout won't work. Let's understand what is static library. A static library is basically a collection of compiled object file bundled together into a single file. On Linux, it's usually have .a, and on Windows a .lib file. When you compile your program and link it with a static library, the code from the library get copied directly into the executable. This means your final binary have everything it needs, no external files required at runtime. Now the question arises, why do we even bother creating static library? Well, the main reason is reusability. Imagine you have a set of functions, say math utils, string manipulation helper, or file handling routine that you use across many projects. Instead of copying those .c or .cpp file into every project, you just copied them once into a static library. Then whenever you build a new project, you just link this library. Second big reason is faster build. If you have 10 different programs, depending on the same utility of the code, compiling it again and again would waste time. With static library, you compile once and then reuse it everywhere. Another advantage is independence. Static library are embedded directly into your executable at compile time. That means once you have built your program, it does not need any external dependencies. Let's create a simple static library. Let's take an example of in a compiler or system development, we often write a small helper utility that we reuse everywhere. For example, a function to check if a word is valid identifier, a function to check if a word is reversed keyword, or a function to trim white space around the tokens. If you copy this into every file, it becomes messy and hard to maintain. So instead, we collect them in a static library and just link it whenever needed. Now it's time to build our first static library. We will call it as libstrutils.a and it will contain a few handy string utility functions. This is our header file. It only contains a function declaration, also called prototype. Any program that wants to use our library will include this file with include strutils.a. The compiler knows this function exists and what their signature look like. If you have noticed, there is include guard at the top. This makes sure that file is only included once per compilation. Avoid duplicate definition errors. We include string because our function uses std string. So strutils.h is like a contract. It says, here are the tools you can use. Don't worry about how they work inside. Just trust they exist. And then our logic implementation, strutils.cpp. So basically, it consists of three functions. This file actually contains the implementation of the function declared in the header file. At the top, we have included strutils.h, so the compiler knows we are defining the function promised earlier. Let's break it down. The function is valid identifier. Check if a string follows the rule of a C-like identifier. Must start with a letter or underscore, followed by a letter or digit or underscore. Also make sure that the string is not a reserved keyword. Trim, it removes the space, tabs, or new line character from both ends of the string. Useful in compiler because source code often have extra white space that doesn't matter. Case keyword, look up the string in the set of reserved word like int while return. If found, return true, otherwise return false. You notice the keyword set is marked as static. That means it has internal linkage, so it's private to this file and not exposed outside. So together, strutils.h is the blueprint what function exists and strutils.cpp is the construction how they work internally. Later we will compile them into a static library that any program can link and reuse. Let's compile our code into the static library. This is a two-step process. First, compile into an object file, then archive into a .a file. Got it? So basically here, to create object file, we use a flag -c with our compiler. Clang ++ -c It compiles the source file into an object file. It will generate strutils.o without linking. Then we archive it using AR and use the flag RCS. What this will do, it will collect the object file and pack them into a static library lib strutils.a. To insert object file in the archive, C create archive if it does not exist, S write an index so that linker can find symbol quickly. On Linux and Mac OS, static library uses the .a extension. On Windows, the same process produce a .lib file. At this point, our library is ready to use. Let's now create a simple driver program to test our library. Here we have included the header file strutils.s to use the library function. Notice we don't write the function logic again, just call them. These keep our main program short, clean and focused. Now we compile and link with our static library command on the screen. Here -l tells the compiler to look for the libraries in the current folder. -l path. So dot means current folder. If I give dot, then I have to go in the previous folder. So or we can give here custom path with -l. -l srutils, this links lib strutils. The compiler automatically adds libs prefix and .a extension. The result is an executable mini compiler. This result shows exactly how helper utility is packed in a library and can be reused in compiler frontends or any parsing program. In the next video, we will explore dynamic library and we will see how they differ from static one and why they are so powerful when building modular system.